This morning, we're going to start off this day of content by talking about, I should get my clicker here, by talking about best practices. Best practices. We all love best practices. It's the wisdom accumulated from long and varied experience. Best practices help us get things done safely, efficiently, and effectively. Much of what we talk about in a conference like this is best practices. I mean, take web apps, for example. Many, perhaps even most of our web apps today look something like this, right? You have kind of a standard three-tier design of front ends, JavaScript, mobile app, what have you. Talks HTTP, probably REST to a back end. You have workers that are probably stateless, and they talk to a database. That's a separate tier database. Now, there's a lot of benefits to writing your apps this way, to design your apps in a standardized way. Some of them are obvious. But one of them is when it comes to deployment, your app will fit well. Right? Your app fits well with the tools in the ecosystem. You fit well with Kubernetes. You fit well with serverless. Your app fits into the cloud ecosystem. And so you have all these resources available to help you deploy, scale, secure, manage your app. If it's a conventional three-tier stateless app, if it follows those best practices. So, best practices, very important. In this session, we're going to throw those best practices away. We're going to talk about those times when we just have to chuck the best practices. We need to push the boundaries and break out of our conventions because we need to create the next new thing. So of course, when you do that, when you break convention, you start to lose that fit, right? You start to lose that fit. Tasks like deployment, integration with other systems become more challenging. I'm going to tell you about an app that I worked on where it didn't follow a lot of those conventions that we're used to. I'll talk about the journey that I took to make it work, make it fit in the cloud. We'll talk about some other platforms that don't follow conventional cloud practices and how they're adapting to the cloud. And we'll talk about how your unconventional apps, some things that you can do to make them fit in the cloud. Now, of course, this is not going to be like an exhaustive survey of all the different things that you can do. I mean, there's just no way, right? We're going to focus on just a couple of examples, a couple of ways that apps sometimes break the mold. And the techniques that we're going to discuss here are also not they're not the end-all and be-all. They're not the final say here. They may work well for some apps. They may be a terrible idea for others. So rather, the goal here is to take a look at some examples, and just get some ideas flowing so that your creativity can get unlocked. So as you are faced with deploying your unique app with its unique challenges, you have a starting point. You have kind of a starting point and some ideas that can stimulate your own thinking. Okay? So quick introduction before I get too far. My name is Daniel. I work at Google as an engineer on the Ruby team. Any Ruby developers here? Ruby? Okay, a few of you. I work for you. My job is to make the cloud better for Rubyists. My team works on API clients, runtimes for App Engine, developer tools, tutorials, documentation, basically everything that you need in order to make the cloud work for Rubyists, for you as Ruby developers. And we're part of a group of teams that focus on different programming language communities. So I work on Ruby. I also do some work on the Elixir programming language. Any Elixir developers here, by the way? One? Oh, awesome. How about Erlang? Erlang is another related language. Any Erlangers? No? Oh, great, great. You guys do anything on Google Cloud? with Elixir and Erlang? Starting to? Great. Yeah, so we're doing a little bit with Erlang now and a little bit with Elixir. It's a lot of fun. I've been learning Elixir myself for the past 4 years or so. But for the rest of us, we have an opportunity now to learn something new, so that's great. Elixir and Erlang are both closely related languages. They're both functional programming languages. They both target a platform called OTP. OTP is part of the platform. There's a bunch of related components. There's a VM, there's a runtime system. OTP relates to the library, the standard library and frameworks associated with the platform. But it's a really interesting platform for web development. It has powerful features around concurrency and around distributed systems. And it also has some really interesting features around fault tolerance and error recovery. But on the flip side, Erlang and OTP, the architecture of an app written for this platform can be different from the way that we're used to writing web apps in other languages like Node.js or Ruby or Go or anything else. And this difference is something that I first encountered when I was first learning Elixir. I had joined a study group with some friends from a local meetup. This was about 4 years ago. And we did a book study in the study group. And then 4 of us got together and we said, let's put some of the things that we've learned into practice and do a project together. So we did this project. This is a screenshot of what we built. As you can see, it's a simple multiplayer tank game. We wrote it as a web app, and you've probably seen this sort of thing before. You drive a tank around a maze. You have other players that are online with you, and they're driving around tanks. You try to shoot them down. So it's online, it's multiplayer, it's real time. Now, none of us were professional game developers. Right? This is the first time that we've done something like this. And we're trying to learn that at the same time we're learning Elixir. So it was a lot of fun. It was a challenge. But we had to figure out a bunch of things while we were doing this. Right? And in particular, we learned that doing this kind of thing as a web app presents some challenges. We figured out early on that the game logic, keeping the game state, tracking the objects on the screen, doing collision detection, all that stuff, it has to be run over here on the server side because we have multiple players, multiple clients connected. So we need some central source of truth for what's going on. So that means we have to stream updates across to the clients. So this is an action game. This is a real-time game. We want 20, 30 frames per second. So REST requests, HTTP, not going to work. Too much latency. So we changed that to a WebSocket, right? And in general, we started to tinker with this web app architecture. We started to change things around because of what our use case was, what our requirements were. We looked at the game logic itself, and we realized, OK, this is a long-running game simulation that we're running here. This is a background process that's continually updating the game state frame by frame. And so it has to operate pretty rapidly, again, 20, 30 frames per second. So if the game state is kept in a separate database, again, probably too much latency. So we chucked the database, and instead we kept the game state in memory in our back-end servers. So now imagine we've got this game simulation running on one of those servers, say this one. Now, there's no guarantee that it's the same server that all the players' WebSockets are connected to, right? The load balancer is just connect the client to whatever it connects it to. So we were thinking, OK, how do we deal with this? And there are a few ways. You can bypass the load balancer. You can customize the load balancer. Or you can let the servers talk to each other. Make our back-end servers part of an interconnected cluster and so that they can forward messages back and forth to wherever they need to be. So again, we were tinkering with the app architecture. tinkering with it, and we ended up landing on something that looks kind of like this. And we say, yeah, okay, this will work. This will work. This will work for our tank game. And turns out that Elixir and OTP support this kind of architecture quite well. They have stateful processes, state kept in memory. There are nodes that are interconnected that can forward messages back and forth to each other. This kind of real-time distributed system is the kind of thing that Elixir, that OTP are particularly designed for. And so as we were learning OTP, as we were learning Elixir, this is how we ended up designing our app. So a little bit unconventional compared with most web apps. So all this was going well. We had our game. It was working. It was playable. We were having fun, the four of us. And we decided, OK, let's demo it to our meetup group. So let's get the whole meetup group together, and they could all connect up, and we can play the game together, and we can show them how it works, how we developed it. So that was a great plan. Now we had to decide how we were going to deploy the game so that people could connect up to it. Well, this was 2015, 4 years ago. And this is a time that saw the emergence of a really interesting deployment technology. Kubernetes was interesting and important at the time it came out because of the way that it oriented the industry around container practices, the way that it codified the practices of container-based deployment. Technically, Kubernetes is a very flexible system, and we'll talk a little bit about that a little later. But in practice, its usage is actually pretty opinionated. Conventionally, Kubernetes wants your servers to be stateless, not stateful. It wants them to be transient and not persistent. It wants them to be independent and not interconnected. This didn't match the way that our app was designed, right? You have Kubernetes stateful sets also. They were called pet sets at the time. But even those didn't quite fit with what we were trying to do. We were keeping state in memory as these long-running processes. So when we tried to deploy our tank game using Kubernetes, we ran afoul of some of these opinions. And at the time, we said, let's just punt on this. We just wanted to get something working for our meetup. So we punted on it. But it does bring up a very interesting and important question. And it's something that we eventually came back to when we started thinking about how would we really deploy this if it were a production application. We started asking ourselves, is Kubernetes, even though it's embodying what's now kind of becoming cloud best practices, is Kubernetes just not the right technology for deploying an app like this? Are containers just not the right technology? Is the cloud itself, cloud best practices, just not designed for apps like this? And we were not alone in asking some of these questions. The Elixir and OTP community as a whole has been debating this quite a bit over the past few years. There's a feeling that containers and conventional cloud practices just don't fit with the way that our apps look. Because of this, the OTP community has been kind of slow in adopting the cloud. So later, when we came back to this question, we started thinking, okay, if we wanted to deploy this to, say, Kubernetes engine, what would we do? What should we do when our app breaks the rules, when our platform breaks the rules? Can it be done? Can I deploy this to GKE and actually have it work reasonably well? So let's take a closer look at this app. And where does it not fit? Where does it not fit with the cloud, and what can we do about it? Well, first, the workers in our app are interconnected, right? They form a cluster. and they have to talk to each other. So now, of course, normal Kubernetes practice is for replicas to be independent, right? But let's set normal practice aside for the moment. If your workers need to intercommunicate, what does that mean? Practically, that means they need to know where each other are. You know, they need to know how to reach each other. They need to have each other's IP addresses, any credentials that they need to talk to each other. There are ways to get that sort of information. Most of us treat Kubernetes as a deployment tool, but it really is first and foremost an API, right? It's an API that you can use to build deployment tools, to build ops tools. It provides all sorts of useful information about the shape of your deployment. And you can talk to this API from within your app. So that might look something like this. This is Elixir code. It's adapted from our tank game, so don't worry about the details here. I just want to point out a couple of things. Kubernetes provides you with your pod's service account credentials, the credentials you need to talk to other things in the Kubernetes cluster, in the Kubernetes ecosystem. These are available in the file system. So we're setting the path to those credentials here as a constant. Kubernetes DNS also provides the domain name. It exposes the domain name for itself, for its own API endpoint. So we're setting that constant. And we can use that information. We have everything we need to send requests to the Kubernetes API from within your app. So this code, for example, returns a list of the IP addresses for all the pods in your deployments. So once you have those addresses, pods can reach each other. So what if, as each pod in your Kubernetes deployment spins up, as each container spins up, we ran that code during initialization? We contact the Kubernetes API. We get a list of all the other pods running, a list of IP addresses. And then we can use that to establish any connections that we need to add that new worker to the cluster. Right? We run all that during initialization. Now, when a worker is shutting down, we want to remove it from the cluster. So we might need to do some disconnection, some cleanup. And again, you can use tools that Kubernetes gives you, such as lifecycle hooks. Now, many of you are already familiar with this. You can configure your pods and your containers with a pre-stop hook that gets executed when that pod is terminated. You can also trap the term signal that's sent to your container when it gets terminated. So you have these initialization and these shutdown hooks available, and they can enable your app to maintain an interconnected cluster like our tank game needed. Okay? This is a pretty common use case for Elixir developers, so the community has developed a library for it. But even if you're not an Elixir developer, and I know most of us are not, if your app needs information about its own deployment environment, just a little digging into the Kubernetes API will yield a lot of useful information. All right, so far pretty straightforward. What else is our app doing differently? Well, our workers are hosting these long-running processes, these long-running game simulations that keep state. Not only keep state, they're not just stateful processes, but they're keeping state in memory. So why is this an issue? Well, most normal deployment practices assume that you can bring down a container at any time. Right? You can bring down a worker at any time. They assume that backends are transient. They assume backends are stateless. And we're breaking those rules because we're running these game simulations in memory. And so when Kubernetes wants to take down that container, say it wants to scale down, it wants to do a rolling update, we have a problem. Unless what if there was a way to move that running game to a different worker? This is a technique known as process migration, moving processes or state from one node to another in a distributed system in general, maybe within a cluster of workers within Kubernetes. There are a number of different forms of process migration. There's been a lot of research done into it over the years. But in our case, it's fairly simple, fairly straightforward. First thing you need to do is you need to be able to checkpoint a process. You need to be able to pause it, you need to capture its state and serialize it. Now, for a game simulation, conceptually, this is not that difficult. Your process is just this long-running process that's updating the game world frame by frame. So you just need to capture one of those frames, capture that as a big data structure. And OTP actually provides you with a number of tools that help with that, capturing, managing, serializing state. So next thing is you need to be able to move that state elsewhere and continue running the process. One straightforward way to do that is to use a message queuing service. So when a node is about to go down, remember we have those Kubernetes shutdown hooks, right? So we use that. You pause the game, pause any games. There might be multiple games running on that node. We serialize their state, and then we push them up to the queue. Then some other node in the cluster can pull those games down from the queue and resume running them. So now we've effectively moved that game from one node to another node. And there are, of course, a number of queuing systems available for you to use. There's RabbitMQ, there's Apache Kafka. If you're using Google Cloud, you might just use Google Cloud PubSub. And here's what that would look like. You can create one topic for process migration. You use a single shared subscription for all the running nodes to listen to. And when a container is about to go down, you serialize games, publish those game states up to that PubSub topic. Each of those games will then get pulled down by one of the other nodes that's listening in on that subscription. Since we have a single shared subscription, it will distribute games among all the listeners. So if you want to implement a system like this, PubSub might be a reasonable way to do it. There are a few things to watch for, some things that we encountered. If you're familiar with process migration in general, you probably know that one of the big challenges is maintaining communication. Maintaining communication. If you have a communication channel with a process, say you're a player connected to a running game, and that game moves to a different node, what do? Right? How do you reconnect to that game? How do you find the new location for that process? One way to handle this is to create and maintain a kind of address book, a mapping from a process ID or a name or some kind of identifier for that process, for that game, say, to the location where it can be found. In Elixir OTP, this is handled by a construct known as a registry. So that's something that we use for our tank game. You could use a low latency database like Redis. You could use some distributed state mechanism like a CRDT. Anything that you can use as a shared, consistent source of truth. So keep an address book so that you can forward messages, so that you can reconnect anything that needs to talk to those processes that are moving. Another issue to consider is load balancing. If you use Google Cloud PubSub, for example, it'll approximately load balance across the listeners that are listening in on this shared subscription. But there aren't guarantees here. So if you want more control, or if maybe you need to distribute load based on the actual CPU load on those workers. So it'd probably be a good idea to do something like monitoring load. You can use a product like stack driver monitoring. There are third-party solutions for that sort of thing. Based on that information, then you can selectively enable or disable listeners, or you can send NACs as necessary. Some other queuing systems also have some interesting features that can be helpful for something like this. If you're using RabbitMQ, for example, subscribers can specify a priority. So you can set a priority based on, say, the load on your worker. Okay? One other item. Depending on the queuing system that you're using, it might be possible under rare conditions for a message to get delivered more than once. This is possible under Google Cloud PubSub, sometimes possible under other queuing systems. So you might need a mechanism to detect and resolve this case. And that's another case where a process registry can help. Because it's a shared source of truth, it's just, for where a process needs to be running, then you can use that to resolve who wins if multiple workers try to pull down a process. Okay? So just a few considerations to be aware of. All right. So we've talked about queuing systems as a way to do process migration. And they're a common way for process migration, but they're not the only way. Our tank game was written in OTP, in Elixir. And that ecosystem actually has access to a lot of really interesting tools for writing distributed applications, distributed systems. You could take advantage of tools in the platform that you're writing for, the ecosystem, to build process migration directly. So this is actually what we ended up doing. We wrote our own process migration in Elixir, and it turns out that there are some nice libraries available in the ecosystem as open source that did most of what we needed to do. So again, most of us aren't Elixir developers here, so I won't go down that rabbit hole describing all of that. If you are interested in a deeper dive in some of the things that you can do, you can look for this talk that I did at ElixirConf last year. It's on YouTube. But in general, there are multiple ways that you can implement something like this. And there are some trade-offs, of course, between different implementations. There are performance versus complexity trade-offs. One of the reasons we rolled our own and did that within the Elixir ecosystem, we passed messages back and forth as OTP messages. And one of the reasons we did that was performance. We actually got really, really incredible performance out of that. But it did mean that we had to do some custom code, so there are some trade-offs. There are reliability concerns, security considerations that you might need to think about. So you'll need to vet those concerns for your app, depending on your particular use case. But in general, for a tank game, we found process migration really interesting. It's a really interesting thing because it actually let us have it both ways. Let us have it both ways. It let us build an unconventional app. It had a stateful backend, processes in memory, all the performance and interactivity benefits that came with it. And it let us deploy that with conventional cloud practices, with conventional Kubernetes. And we got all the auto-scaling, all the CI/CD benefits, all the cloud kind of management and ops benefits that come with that. We got it both ways. So it was a really interesting exercise for us, and we learned quite a bit. Of course, it is possible that process migration in particular is not appropriate for your app. Some workloads might not lend themselves to pausing a running process, snapshotting and serializing. Or performance might be an issue. For our tank game, we got really good performance out of it. Maybe a few tens of milliseconds in order to migrate a game. So it was totally fine for our application. People's internet connections will lag for more than that. But maybe your app has more stringent real-time requirements. So let's take a look at some other ways that you can deal with things like this, with in-memory state. Now, if you're working on a large-scale, say, multiplayer gaming system, professional gaming systems often divide servers into separate pools. You have a set of servers maybe that are for normal web-like requests, so things like profile pages, lobbies, and so forth. And these can be managed and deployed with familiar techniques, right, like Kubernetes. But maybe game simulations, maybe you need to do games like as long-running background processes, state in memory. And maybe those things can't be interrupted. So you might want to run those on a separate pool of servers that are orchestrated differently. So if you have some servers that follow a different set of rules, Can you deal with that? What can you do about that? Well, fortunately, as we mentioned before, Kubernetes is a highly flexible system. It has opinions, but it can be customized to implement different sets of rules, even within kind of the same overall deployment. Agonase is a project that has taken advantage of that. Some of you have heard about this. We've talked about it in some of the other sessions. It provides tools to manage dedicated game servers, matchmaking some of the various needs of a gaming system. It's being developed jointly by Google Cloud and Ubisoft, which is a large game developer. So it's well worth checking out if you're interested in working in high-performance gaming or anything else that might be really similar. Okay. Sorry. Okay, let's take a look at one more example. One of the more interesting features of Elixir and OTP is hot code upgrade. Hot code upgrade. The OTP platform actually has the ability to hot upgrade your code while it's running. Right? You can have a code base running code, and then it can seamlessly translate to a new code base while that code is running. Does that seem far-fetched? Why would you ever need to do something like that? Well, hot code upgrade comes from OTP's roots as a telecom platform. It was originally developed by Erlang back in the 80s, or by Ericsson back in the 80s. They developed the Erlang language and the OTP platform. They developed it for things like applications like switches. Say you have a switch that's in the middle of running live phone calls. You have software running on that switch. You can upgrade, if you want to upgrade the software on that switch while those calls are running. You don't want to disconnect your customers. You don't want to interrupt those phone calls. So capabilities like hot code upgrades were developed during this time. And it's a really powerful capability, but it does seem to be kind of contrary to what we usually do in the cloud, right? We kill old containers and we spin up new ones. So what if you wanted to use something like hot code upgrade in the cloud? What if it seemed appropriate for your app? And there are apps that could take advantage of something like this. Well, here's how one service is solving this problem. Jig Elixir is a platform as a service. It was designed especially with Elixir and OTP applications in mind. It's not a Google product, but it has some really interesting ideas. They realized that containers and kind of conventional cloud practices, container orchestration, is still valuable, still usable for managing your cloud resources and for doing things like updating libraries, updating your OS, updating your dependencies. But containers don't work so well for hot upgrade, for updating software in place. So Jig Elixir developed a hybrid approach, and it looks kind of like this. In traditional deployment, you might create a build of your app in Docker, right? So you have all the dependencies, the OS, and your app all in a single Docker image. And this is what you deploy to Kubernetes, to Cloud Run, for example. Now, Jig Elixir modifies this. They separate your app from the OS and dependencies. So they still build the OS and dependencies in Docker, but the app is built as a separate image. And it gets mounted into the container as a volume. So since your app lives on a separate volume, it has the ability to modify itself on that volume, even though it's running in the container. So now we can perform hot code upgrade without taking down that container. Then, of course, if we want to make these larger but less frequent changes to the OS or the dependency layer, these can be done using familiar Kubernetes techniques. So again, a hybrid approach. Hybrid approach. This is just another way that a service has found creative ways to meet the needs of unconventional apps while continuing to fit into kind of a cloud ecosystem. All right, what have we learned here? What have we learned? Well, we've seen just a few techniques that might be useful. for deploying unconventional apps, particularly stateful apps, real-time interactive apps. We saw that you can use the Kubernetes API to query your deployment environments. We saw that how we can use that information to establish communication among your server replicas. So if your server replicas need to forward messages to each other. We saw some ways that you can use process migration to preserve server-side state, even to preserve running server-side processes when you redeploy your backend. We saw how some projects are extending the Kubernetes infrastructure, and others are using hybrid techniques to meet the needs of highly interactive apps. In general, we've seen that you don't need to throw away our tools and our best practices. Right? Often we just need to stretch them a bit. We just need to add to them a little bit. And this is important. It's important to think in terms of stretching, because it's this process of stretching our practices that could be the basis of the next generation of our cloud tools and our cloud deployment practices. And maybe even the evolution of the cloud itself. I mean, take serverless, for example. There's a lot of talk about serverless these days, right? A lot of talk, a lot of excitement, maybe some skepticism. Today, serverless is often equated with functions as a service. Now, functions are awesome for some workloads, but I mean, let's be real, won't work for our tank game, right? But functions are not the end-all and be-all of serverless. And we've seen that during this conference in Cloud Run. Cloud Run expands what's possible under the umbrella of serverless. It expands it beyond functions, just functions per se, just a bit. What if we were to take that a little bit further? What if we were to imagine a future serverless where we could even have stateful processes coexisting with stateless functions? What could that look like? What should it look like? Would it support process migration? Would it support game servers? Would it support hot code upgrade? Would it look totally different? Maybe it would be a terrible idea. I don't know. I don't think anyone knows yet. But I think that's the fun part. It's the fun part of where we're at right now in cloud. And it's the kind of question that can and should be driven by our unconventional apps, by apps like our tank game, by apps that you are developing today. That's why I love being around technologies like Elixir and like OTP and the communities that are around those. Developers like you who are pushing the envelope, who understand that it's okay sometimes to be unconventional, because you are the ones catalyzing those changes, the next generation in cloud, coming up with the wild ideas, stretching our best practices, and creating more powerful tools and moving the industry forward, right? Because we know that what's conventional today might not be adequate for tomorrow. So here we've talked about just a few ideas, just a few techniques that might be useful, or at least maybe interesting, maybe. I'm sure you have your own ideas. That's the point here. I encourage you to come up with your own ideas, to share them. Get involved. This is your cloud. This is your cloud here. This is your community. I want to hear your ideas. Your colleagues here want to hear your ideas. Google wants to hear your ideas. You know, what will things look like beyond that horizon? Let's move the cloud forward together. Thank you for coming.